Good afternoon, everybody. Yeah, it's really a great pleasure to have Manasvi Lingam today for our seminar. Manasvi got his PhD at the University of Austin in Texas, and after that he got postdoctoral positions at Princeton and Harvard and at the Harvard Smithsonian Center for Astrophysics. And he's currently an assistant professor in astrobiology at the Florida Institute of Technology. And today his talk will be about how the star impacts the habitability of planets. So thank you, and I leave the floor to Manasvi.
Thank you for these kind words, for the kind introduction, Amedeo. It is my pleasure to be here, and I hope that everybody is doing well in these troubling times. And so let me get started with my presentation. So as the title indicates, I want to talk a little bit about some of the various ways by which the host star can impact the habitability of the planets in that particular planetary system. So let's get started. So I will try to go over three different areas depending on how time permits. The first one I will talk mostly about photosynthesis and how the type of the host star can have a fairly major influence on photosynthesis. And the second one will be on atmospheric escape, namely how do the stellar winds, flares, and so on, how do they mediate the rates of atmospheric escape. And the third one, I will speak about prebiotic chemistry mediated by the emission of high energy particles from the sun during what are known as solar or stellar proton events. And so let me get started. So not everybody might be familiar with what is astrobiology, so I would like to begin with the standard NASA definition. Astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. This multidisciplinary field encompasses the search for habitable environments in our solar system and habitable planets outside our solar system. And in this talk, I will be covering mostly the latter. And here we can see one more illustration of the various domains that fall under astrobiology, so which starts from Earth, so it includes the origin and nature of life on Earth itself, and then of course it includes objects in our solar system such as Mars, Europa, Titan, and so on. And then looking further beyond, it also goes on to deal with exoplanet biosignatures. So as I said, the bulk of my talk will be on exoplanets. So just this is more of a reminder for everybody, since I think many will be familiar. So extrasolar planets are also known as exoplanets, and these are planets located outside the solar system. And currently we have over 4,300 exoplanets, and this number is continuing to grow at an exponential rate. And just to give you a couple of discoveries that have been found in the last few years, one of them is Proxima Centauri b, which orbits the star Proxima Centauri, which is an M dwarf. So it's a cool star, a small star that is about 12% the mass of the Sun. And it's the nearest star to Earth, hence the significance of this planet, because it's located only about 4 light years away, so a little over a parsec away. And the planet's mass is known to be greater than 1.27 times the mass of the Earth, and it orbits, and the orbital radius is about 5% that of what we see, 5% that of Earth's orbital radius. So its semi-major axis is 0.05 AU, and then of course, this other planetary system which caught a lot of attention is the TRAPPIST-1 planetary system, which consists of 7 roughly Earth-sized planets which are orbiting the star TRAPPIST-1 at a distance of 40 light years away, so around 12 parsecs. And the mass of this star is again very small. It's about 9% the mass of the Sun. And here you can see some of the other properties of the planets which I won't be touching on. And so, of course, I have emphasized the word habitable a few times. So it's good to spend the time, a little bit of time, talking about the habitable zone. And what is the habitable zone? The habitable zone is essentially the region around the host star where liquid water can theoretically exist on the planetary surface. Sometimes it's also known as the Goldilocks zone. And roughly about 10% of all stars in the Milky Way are expected to have an Earth-sized planet in the habitable zone, but there is some uncertainty on this front because we don't have a large statistics yet. And in this particular plot, you can see some of the famous planets. Here we have Earth. So the blue region is essentially the habitable zone. And one can see that the Earth is located here, so is Mars. And if one looks at the very bottom, so if you look on the y-axis, we see 3000 Kelvin. So if we follow along this axis, we can see the TRAPPIST planets here. So there are three of the TRAPPIST planets that exist in the habitable zone, E, F, and G. And then there's also Proxima Centauri B. So these are some of the well-known examples of planets in the habitable zone, and there are of course several others such as Kepler 62f, which is just below Mars, and so on. And so, as I said, I'll be talking about how the star impacts the habitability of the planets. And this, of course, brings up the question, why should we care about stars? So let's recall the definition of habitability. So habitability, again, in the NASA astrobiology documents, it's defined as the potential of an environment, past or present, to support life of any kind. So it is a concept that clearly pertains to planets and also to moon. So of course the question is, why do we want to care about the host star at all? And to put it in a somewhat different way, we can ask, can the properties of this host star influence how the likelihood of the origin and evolution of life on planets? And in this particular talk, I will be going over three different areas where it impacts the where the star impacts the habitability of the planets orbiting it. So the first one that I will be talking about is electromagnetic radiation, specifically oxygenic photosynthesis. So electromagnetic radiation actually has a number of different impacts on the habitability of the planets in both positive and in negative ways. What I have here is essentially a figure that is taken from a review paper that was published with my collaborator from Harvard in 2019. In Reviews of Modern Physics, you can find the details here. And there are many different effects that exist that arise from the availability of this electromagnetic radiation in different bands. So UV radiation, ultraviolet radiation has some effects, both positive and negative. X-rays and hard ultraviolet, extreme ultraviolet radiation has other effects. And then there's also what people call the photosynthetically active radiation, which is roughly between 400 to 700 nanometers, at least for oxygenic photosynthesis. And that, of course, is the one that I will be focusing on. And so let's go to photosynthesis. Of course, we all know from our basic biology that photosynthesis is, in many ways, either directly or indirectly, the basis of all food webs on our planet. It is the most common source by which, organisms take energy from the sun and then they use it to synthesize biomass, and then this biomass is consumed by other organisms either directly or indirectly, and that of course forms the basis of a biosphere. Now there are many different types of photosynthesis around. The one I will be focusing on is called oxygenic photosynthesis, and this is also the standard version of photosynthesis we know, namely where you have the production of something like sugars, and then you also have oxygen being released as a byproduct, hence the name oxygenic photosynthesis. There are also other versions of photosynthesis known as anoxygenic photosynthesis, and in there, instead of using water as the electron donor, there are other compounds that are used. So as I said, here is of course a very simplified representation of the oxygenic photosynthesis reaction, where you can see there is carbon dioxide and water that are collectively giving rise to the sugar and then to oxygen. And this oxygen, of course, is what gives it the name. So we can see that this process of carbon fixation, which means it's essentially taking inorganic carbon in the form of carbon dioxide and then synthesizing organic compounds. This process of carbon fixation clearly requires photons, as you can see from this H mu that I've highlighted. And of course, the thing is that the stars of different masses have different temperatures, and in other words, they all have different spectral energy distributions, which means they emit different amounts of radiation across the various ranges, and therefore this will affect the likelihood of sustaining biospheres with productivity similar to that of Earth. And by productivity, what I really mean is the amount of biomass that is being synthesized per unit time through this process of photosynthesis. So this has been studied in a few publications. Here are a couple of them. So the first one that I have shown here is essentially the photon flux for an Earth analog as a function of the stellar mass. And what do I mean by an Earth analog? It is essentially a planet that is in all ways resembling that of Earth in terms of the total stellar flux it receives, in terms of the size, in terms of and in terms of other properties as well. So therefore, the only thing that is being changed, because the purpose of my talk is to illustrate how the star impacts habitability, the only thing that is being changed is the stellar mass, or equivalently the temperature. And this, of course, will result in radiation, in the radiation profile changing from one star to another. And what I show here on the y-axis, one has the flux normalized in units of the flux that one would need, the stellar flux in the photosynthetically active range of 400 to 700 nanometers. So what it does is it shows the flux normalized to the value that we need in order to sustain a biosphere similar to that of the Earth. So if the blue curve goes below the red line, which happens in this range, in this small mass range, then in principle it would not be feasible to support a biosphere with the same productivity as that of Earth. So this calculation, as I said, the only thing it does is it changes the nature of the star. There are many other limitations that dictate the productivity of a biosphere, such as nutrients and also the temperature, which I will get to a little bit later. So here what we see is that if you have a star with mass smaller than roughly 20% the mass of the sun, then it would be unlikely for a planet orbiting that star to have a biosphere that has the same productivity as that of the Earth. And so why do we care about oxygenic photosynthesis from a pragmatic standpoint? And the answer is that oxygen is, as we saw, one of the products that comes from oxygenic photosynthesis. Therefore, the whole goal of one of the major consequences of oxygenic photosynthesis is that it liberates atmospheric oxygen, and also that oxygen can react with ultraviolet radiation and give rise to ozone. So the oxygen and ozone levels in the Earth's atmosphere, for instance, are a consequence of oxygenic photosynthesis. And therefore, these have been regarded as promising biosignatures. So one essentially wants to understand on a given world, so if you have a planet around a different star, can it accumulate enough oxygen to be detectable, for this oxygen to be detectable? And what we have here in this plot are some of the features that exist for oxygen. And there are a number of features around 0.7 microns, which are particularly well known. And so oxygen and ozone therefore have distinct spectral features, and they have been studied as promising biosignature candidates for a long time. And of course, there are some subtleties here that I will not get into, such as false positives, false negatives, etc. So, therefore, one of the major implications of oxygenic photosynthesis is that it can give rise to, it can essentially give rise to oxygen, which is a potential biosignature. And therefore, we can ask ourselves, under what conditions will this oxygen accumulate to sufficiently high levels in order to be detectable by upcoming telescopes? And so if you have insufficient production of oxygen through photosynthesis, what this can happen is that the atmospheric oxygen that is being pumped into the atmosphere through photosynthesis and other processes can be depleted by the sinks that exist, such as gases produced by volcanism, weathering, and so on. So what can happen as a consequence is that life may exist, but oxygen, which is this prominent biosignature, may not be detectable. So one can essentially look at the criterion where the sinks, where the sources dominate over the sinks. So what I have in this plot is the ratio of the oxygen sources to the oxygen sinks. And when that ratio exceeds greater than 1, then oxygen can accumulate in the atmosphere, and that can lead to the manifestation of a detectable oxygen biosignature. And this criterion, where you exceed this red line, is satisfied for roughly 13% the mass of the sun. So that's the first thing that I want to, that's the first takeaway, that if you have these planets around low mass M dwarfs, the late type M dwarfs as they're called, and that includes both Proxima Centauri and TRAPPIST-1, there may not be enough oxygen that accumulates in the atmosphere for it to be detectable. And so now I want to sort of go to a slightly higher level of sophistication. Well, as I said in the previous analysis, what was done was that the only thing that was changed was the nature of the host star, and everything else was held the same. And this was a very simplified model, because the only limitation, the only constraint that it took into account was the amount of photons received at the surface of the planet. But let's say you have a planet with a substantial ocean. So Earth has about 70% of the oceans, and half of the productivity, half of the synthesis of organic compounds, roughly 50% of the whole synthesis occurs in the oceans through cyanobacteria and other species. So the question is, what if you have a planet that has a substantial coverage of oceans, maybe even 100% ocean? These are called ocean planets and water worlds. So there you cannot just take the photon flux at the surface and then just count the number of photons, because you also have to take into account the fact that this water will pass, sorry, this radiation will pass through the water, and then it will undergo attenuation by water as well as any organisms that exist. So if one wants to compute the flux at a given depth, let's say you want to find the flux F at a given depth, one has to essentially take these various properties into account. You have to take into account not just the flux of photons at the surface, but also this attenuation that comes into play. And so what is shown here is something known as the compensation depth. And the compensation depth is essentially defined as the depth where the rates of photosynthesis for a given organism balance the rates of respiration. So if you go any deeper, what will happen is that the growth rate of, I mean, the energy that is being, in some sense, being trapped by photosynthesis will be smaller than the energy that is being expended during respiration. So if you go below this particular threshold, then it would be unlikely for an organism to survive. And in some sense, this compensation depth can be roughly, I mean, in the crude sense, in a heuristic way, one can treat it as the depth of the photosynthesis zone. And so this black dashed line essentially represents the threshold. So when the solid curves intersect the black line, that's where one essentially has the compensation depth, which essentially gives the depth of the photosynthesis zone. So for the sun, it turns out to be around 20 meters in this model. But if you look at a star, I mean a planet orbiting a star with 2500 Kelvin, then in this case the compensation depth only turns out to be a few meters. So one has, I mean, the depth of the photosynthesis zone shrinks by nearly an order of magnitude, or more than an order of magnitude, when one moves from a planet around a sun-like star to that orbiting a late-type M dwarf similar to TRAPPIST-1. And why is this depth of the photosynthesis zone important? So there are multiple reasons why this is important. One of them is that, so as I said earlier, that oxygen and ozone are both promising biosignature candidates. There's also another well-known signature of oxygenic photosynthesis, and that's known as the photosynthetic red egg. And so what is that? So this is essentially comes from the fact that the chlorophylls absorb strongly at wavelengths shorter than that of red light. So when you reach the vicinity of red light, then the absorption of this radiation goes down, and therefore the reflectivity, the reflectance of these organisms goes up. So for photosynthetic organisms, when you approach the red wavelength, there is a sharp increase in the reflectance. And this is, of course, most dramatic when one inspects terrestrial plants, which you can see in panel A. And in panel B, one can find the similar thing for aquatic plants. And similarly, one can also find it for mosses to some degree. And algae also have an increase in panel E. So this essentially, so what this would mean is that if you have any photosynthetic organisms around an M dwarf, on an M dwarf exoplanet, they could exist closer to the surface because the depth of this photosynthesis zone is much more shallow, and therefore they would be situated much closer to the surface. Whereas if one goes to a star that is even hotter than that of the sun, for instance, then the depth can increase more. So that's one reason why it's helpful. And then the next thing I want to get to is the net primary productivity. And so this is essentially related to the productivity that I mentioned earlier. This encapsulates the net amount of carbon. So it means the amount of carbon that is converted into biomass by photosynthetic organism minus the amount that is expended during respiration and other processes. So it is the net amount of carbon that is converted into biomass, and it's usually measured in per unit time. And on Earth, the most common unit is the amount of grams of carbon that is synthesized per year. And this net primary productivity is a very complex function that depends on the star spectral type. It depends on the amount of nutrients that are available in the oceans and so on. It also depends on the temperature. And so the temperature is something that most studies don't really think about in much detail, but it can have a fairly strong impact on the productivity. So what we have in this particular figure is the relative net primary productivity. So this means that it is the net primary productivity for a planet normalized to that of the Earth's oceans net primary productivity. And one can see that for a good range of temperatures, it is not changing a lot, but once we get to around 30 Celsius, at least using the Earth's organisms as a proxy, it undergoes a steep decline and then it becomes really small. And this is the solid black curve is for an Earth-like planet orbiting a sun-like star, a solar twin, whereas this dotted line is for a planet orbiting a late-type M dwarf similar to TRAPPIST-1. So we can see that for the TRAPPIST-1 like planet, the net primary productivity is really very small. It's anywhere between 10% to it can reach at most 10% that of the Earth. So that's the other thing I wanted to mention. And now we come to So why is this net primary productivity important? So this actually goes to something on a buildup of atmospheric oxygen, and therefore the amount of oxygen that is accumulated in the atmosphere that will depend on whether the sources can overcome the sinks, exceed the sinks, and this can be written as a condition of net primary productivity. It turns out that the net primary productivity has to be about 90% that of the Earth in order for this build-up to occur, assuming that some of the other geological factors are still held the same. So this phi essentially represent the amount of carbon that is buried due to various processes, and d dot represents the emission of reducing gases from volcanism and the weathering of the seafloor of the continents and so on. So what happens is that in order, let's say that one holds these two factors, the last two factors in equation 2, let's hold them fixed at their fiducial Earth-like values, then one would about the would have to be about 90% that of the Earth's net primary productivity, and this would be satisfied only in the range of 15 to 35 Celsius, and after that it drops below it. Whereas if you look at the planets orbiting late type M12, as we saw, the maximum that it can reach is something on the order of 10% that of Earth's NPP. So which means that this particular criterion too would not be fulfilled. So this, of course, illustrates the same point that I made earlier on, that for planets around late the only parameter taken into account was the photon flux at the surface in the appropriate wavelength range. But in this more other sophisticated, in the subsequent models, there were more factors added that I can't get into, but one can find the relevant details in the references cited here. And so there's a number of physiological factors, geological factors, and so on that come into play in basically determining this criterion. So that completes the first part of my talk. And now that brings me to the second talk, namely atmospheric escape. And so before that, I just want to very quickly run through a few concepts which many of you might be familiar. Solar wind is the first thing that I want to, and the solar charged particles from the sun and from other stars, and the density near the Earth is a little bit smaller or comparable to 10 particles per centimeter cube, and the speed of the solar wind again varies by a factor of 2, but we can say that the typical speed is on the order of 400 kilometers per second. And the other thing that I want to mention are the flares. So flares are, of course, energetic explosions on the surface of the sun and other stars. And these are accompanied by a spike, so a rapid increase in the amount of electromagnetic radiation emitted in different bands, so in white light, ultraviolet, X-rays, etc. And here in this figure, one has a picture of a flare, which is the bright yellow region over here. And flares are many times, but not always, accompanied by the expulsion of large blobs of plasma containing both matter and magnetic fields. And these are called coronal mass ejections, CMEs. And they can transport a lot of energy and a lot of mass, as one can see. And what we see here in this figure is an example of a coronal mass ejection. And again, the bright yellow region represents the ejected blob. And the circle that is in there represents the size of the star. So in certain cases, the size of the CME can, of course, exceed the size of the star. So why did I mention these three things? So the reason is that these will all come into play when I talk about atmospheric escape. So So of course, for a particle to escape the atmosphere, by definition, these particles need to gain enough velocity to escape the planet's escape velocity. And as shown in this schematic figure here, if one has a speed that is greater than v escape, then it can from the planet. So in many cases, this energy can be supplied through collision. And this is known as thermal escape because you have different particles colliding, exchanging energy, and so on. But remember, as I said earlier, what one has the stellar wind, which is basically a stream of plasma, and that's interacting with particles in the planet's magnetosphere, which also comprise of charged particles. And when one has a plasma around, of course, there are electric fields that are at play. And these electric fields can also accelerate particles to sufficiently high velocities to enable the escape of this particular of the charged particle. So both stellar winds and coronal mass ejections are capable of driving escape through a number of non-thermal mechanisms, including polar winds, sputtering, and so on. And what one needs in order to study them is sophisticated multi-fluid magnetohydrodynamical simulation. And therefore, the question that one can pose is, how do these winds, flares, and coronal mass ejections impact the atmospheric escape rates, especially for planets around M dwarfs? And one point that I didn't mention early on is that M dwarfs are the most common type of stars in the Milky Way. And also because these stars are smaller, it's easy to find planets around them using the transit method and so on. And one can also, in principle, study their atmospheres relatively easily. So there's multiple reasons why there's an interest in M dwarf exoplanets. And therefore, the question that one poses is, how do these winds, flares, and coronal mass ejections, what impact do they have on the escape rate? And the retention of an atmosphere is crucial in many ways. From the standpoint of habitability, one needs a finite atmospheric pressure for liquid water to exist. Otherwise, it will just sublimate from the ice phase to the vapor phase. So one needs an atmosphere for liquid water on the surface. The atmosphere also provides protection against radiation and so on. And as I said earlier, when you talk about looking for biosignatures in the atmosphere, if you do not have an atmosphere, then by definition, of course, one cannot look for atmospheric biosignatures. So these are the various reasons why one would want to study atmospheric escape. So what we did was we essentially carried out simulations of escape rates for TRAPPIST-1 for the planets of the TRAPPIST-1 system, and then compared them against an analytical model. The results are essentially shown in this figure here. And the escape rates have been normalized in units of the TRAPPIST-1b total escape rate. And the escape rate for TRAPPIST-1b, at least in our model, was found to be on the order of 6 into 10 to the power 27 particles per second, assuming a certain atmospheric composition. So in this first work, we looked at a more carbon dioxide dominated composition similar to early Earth or to Mars and so on. And one can also do the same analysis for a modern Earth-like atmosphere as well. And as I said, the escape rate is close to 10 to the power 28 particles per second. Whereas in our own solar system, there is quite a lot of variability between the escape rates for the solar planet. So it can vary anywhere between 10 to the power 24 to 10 to the power 26 particles per second. So one can see that these escape rates, for instance, for TRAPPIST-1b are a few orders of magnitude higher compared to the escape rates in the inner solar system. And now I come to the effect of the flares and the coronal mass ejections and so on. So one thing I said about flares is that they emit lots of electromagnetic radiation, including in the X-rays and the extreme ultraviolet range. And these particles have enough energy that they can be absorbed by these photons have enough energy that they can be absorbed by particles and further drive escape. And similarly, the coronal mass ejections tend to have a much higher plasma density, higher interplanetary fields, and so on. And they can drive escape through these non-thermal escape processes. So both flares and coronal mass ejections can contribute to the elevation of the atmospheric escape rates compared to the background case where one has only the stellar wind at play. And therefore, the black line that we see here, and this is for the TRAPPIST-1 system, and it was subjected to a flare and an accompanying coronal mass ejection with an energy of around 10 to the power 26 joules, which is 10 to the power 33 ergs. And so what we have here, the black curve is essentially the escape rate for the TRAPPIST-1 system, and then one similarly, but then let's say if you have a flare, we can see that the escape rate is boosted by an order of magnitude, and if one has only a coronal mass ejection, even then it's boosted by roughly an order of magnitude. But if one has both a flare and a CME, then it's boosted by more than 2 orders of magnitude in some cases, or roughly by 2 orders of magnitude. Let's say that if you have a one that is outputting flares at a high rate and also coronal mass ejection and so on, then the escape rates would be even further elevated. And so one can also look at atmospheric escape for planets with different types of atmospheric compositions. As I said, we looked at carbon dioxide dominated planets and so on, but one can also look at other atmospheric compositions. And one of the interesting class of planets which we don't have in our solar system are the water world, where it's expected that the dominant atmospheric component would be water. So what one sees here is the contour plot for the escape of the water ion in cases. The first particular column that one has depicts the escape rate for an Earth-like planet around a Sun-like star subjected to the modern solar wind conditions. The second panel depicts the same thing for early solar wind conditions, so around 4 billion years ago. And the third one depicts the escape, how the escape operates for this planet under a Carrington type event. So the Carrington type event was a large CME 1800. And so the third panel again shows what happens when one has a coronal mass ejection added. And what will happen is that, again, I didn't put the numbers in, but the escape rates turn out to be elevated by about a factor of 100 compared to the first panel where one has the ambient solar wind. And this is the second part of my talk. And now I come to the third one. And so these, as I said, so I'll be talking about this solar or stellar proton event. So what can happen is during these flares, one can have energetic particles that are accelerated at the sites of the flare. And another way that energetic particles can be produced is that they can be accelerated by shock waves that are driven by coronal mass ejection. So again, although it doesn't always happen, in many cases, these flares are associated with this emission of high energy particles, which are called solar or stellar energetic particles. And this sudden influx of energetic particles is known as a solar or stellar proton event. So why are we interested in this solar energetic particle? So, well, one reason is there's been a lot of experiments conducted over the past several decades looking at how ultraviolet radiation can enable prebiotic chemistry. So solar energetic particles are also another source of energy. So then the question is, can they power chemical reactions that lead to the synthesis of biomolecular building blocks on Earth and Mars around 4 billion years ago? So in order to do that, one has to look at 3 different steps. The first one is to look at how much energy is being deposited at the surface during a single solar proton event. Secondly, one has to look at how many solar proton events were happening per unit time. And thirdly, one has to take this particular energy flux and then estimate the rate of production of the biomolecular building block. surface, and this was done for both current and ancient Mars. And what one finds is that for the current Mars, because the atmosphere is more tenuous, surface, whereas for the ancient Mars, assuming that the atmospheric pressure was around 1 bar, then it's much thicker than particles that can make it to the surface must have energies of a few GeV. And one can calculate the solar energetic particle flux at the surface. That number is not provided here. And then for the step 2, to see the frequency of solar energetic particle impacts with the Earth, we looked at the Kepler flaring data for the young sun-like stars and then use certain scaling relations to find what is the energy flux associated with solar energetic particle. So putting the first 2 steps, one finds that this energy flux is around 100 times smaller or even more compared to the other prebiotic sources. Therefore, the question is, do these solar energetic particles even matter? And the missing component is the third step, namely, what is the efficiency of formation of these prebiotic molecules and what is the diversity that can be formed. And there have been experiments that have been conducted to look at the yields of amino acids and nucleobases under and using these particular laboratory experiment, what we found is that the production rate of amino acids on Earth is around 10 to the power 7 kilograms per year, and then for orders of magnitude lower. So how does this compare with other pathways? So one of the well-known pathways is the delivery of these compounds through comets, asteroids, and so on, through meteorites. And in this case, it turns out if you look at the numbers here, 10 to the power 7 versus 300 or 10 to the power 4 versus 2, we can see that the amount of amino acids and nucleobases that can be synthesized through this pathway are potentially 3 to 4 orders of magnitude higher. And then one can ask, how does this compare with the yields from ultraviolet radiation, from lightning, and so on? And it turns out that slightly higher. So this procedure was done specifically for early Earth and early Mars. So this is the one part of my talk which focused more on the solar system as a whole. But one can do a similar analysis for M-dwarf exoplanets. And it turns out that these yields can be boosted for the late type M-dwarfs for planets like the TRAPPIST-1 system and Proxima Centauri b. These yields can be boosted by 3 orders of magnitude, mostly as a consequence of the smaller planet distances, because the flux of these energetic particles declines with the distance. It doesn't go exactly like an inverse square law, but it does decline with the distance. And so as a result, if you're much closer, then the flux of these particles is higher, and then the yields might. Why is this? Because the reason is there's been some papers such as this one cited here and several others which suggest that M-dwarf exoplanets might be hampered because they don't receive enough UVC radiation, which is basically ultraviolet radiation in the range of 200 to 280 nanometers. So they suggest that these planets may not receive enough UVC radiation. Prebiotic chemistry mediated by UV radiation. So it is a possibility that these solar energetic particles, stellar energetic particles, could offset that deficiency to some degree. And of course, more work is needed on this front. This is not a pathway that has been extensively. They have in the past, but there is a need to carry out more experiments involving atmospheres of different compositions as well as different surface pressures. So that basically, takes me to the end of my talk, and I have a few take-home messages that come from the 3 parts. one is that the photosynthesis exhibits a lot of sensitivity to what the spectral type of the host star is. So what we saw was, for instance, that the depth of the photosynthesis zone, or the amount of carbon that is synthesized, biomass that is synthesized, can vary by more than an order of magnitude as one goes from a planet around a sun-like star to one around a lake-type M dwarf, like TRAPPIST-1. And therefore, Earth-like planets around M dwarfs, there should really be an around M dwarf here. They may not accumulate enough biological oxygen in their atmosphere to be detectable. And then the second one is that to properly understand how atmospheric escapes can occur from planets around M dwarfs, one has to study the star-planet interactions carefully using MHD simulation. And what we find is that although there are some subtleties involving the atmospheric composition and some of the less known stellar parameters, the general conclusion seems to be that the escape rates are potentially orders of magnitude higher than those documented for our solar system. So what this could mean is that some of these planets could be depleted of several bars of atmosphere in a time scale of less than 1 billion years. So over 1 billion years, one may lose 10 or even 100 bars of atmosphere due to these particular non-thermal processes. And then the third one is that solar energetic particles more applicable to planets around M dwarfs that receive low fluxes of biologically active UV radiation, that is UVC radiation. And just to conclude with a little bit of publicity, there's, my collaborator and I have written a book that aims to teach astrobiology at the graduate level, and it's available on Amazon. It will be out sometime in the middle of next year. And with that, I would like to thank you all for your attention, and thank you once again for having me.